So, good morning. Anyway, we have something to do today, and that what has been promised to deal with today is nonlinearity. Now, this is quite a tricky issue. First, we are quite happy with linear circuits because they are easy to analyze. We are quite happy with linear media. It's easier to calculate electromagnetic fields within linear media. Unfortunately, there are some elements that could not be realized without nonlinearity, be it mixers, frequency multipliers, detectors, and oscillators at least. In fact, to some extent also amplifiers need a lot of understanding of nonlinearity to produce good ones. So we will have to somehow deal with nonlinearity. And that is something we will talk about today. Due to the amount of time we have available, we will spend but one lecture with nonlinearities and solution of that within CAD programs and calculations. But anyway, let's start with the topic. Well, first I will a little bit switch to circuits because that's possibly more understandable, and I will a little bit comment on two possible approaches, which is time domain versus frequency domain in circuits and nonlinear systems. So first I would like to start with the simplest thing, that is dealing with nonlinear circuits in time domain. This is what programs like SPICE that are readily on the market, and many of versions of SPICE are available for free. So this is what those programs do in principle. We have circuit that contains some elements like a capacitor and an inductor, for example. And such a circuit could be expressed in time domain quite easily. We have some current, let's say here, and therefore we can establish the voltage over the resistor using the Ohm's law. So we know that be this the current here, the voltage over or across this resistor is resistance times current at any instance of time. The capacitor is a bit more difficult to handle because it accumulates energy, so that the voltage that is on the terminals of the capacitor does not directly depend on the current that flows through the capacitor at the instance of the moment, but it is a function of history. In fact, the voltage over the capacitor is dependent on the charge, which is accumulated in the capacitor, so that the voltage there is given by the integral of the current as a function of time, dt, and of course 1 divided by C. The bigger the capacitor is, the lower the voltage would become with the same charge. So we can establish a set of integral or differential equations. We can express this by the same, like the current as a time derivative of voltage. So a circuit could be described by a set of integral differential equations. Within SPICE we choose converting everything to differential equations, and then we would apply time stepping solution of those differential equations. We have addressed that a little bit earlier, so we have already been talking about a way of solution of multiple differential equations. So this is verified. We have an electric circuit. We in any case can express it with a set of differential equations and then solve that. If we provide a solution over a number of discrete time points, we can then, for example, convert that set of points using some interpolation. So this is what the program shows you. You would see a nice line, not a set of points. And then, if desired, and this is time, and this is, for example, voltage, we can convert that into frequency domain using Fourier transform. Now that needs several remarks. First, we have some approximation to the circuit behavior. And today's methods of differential equation solution are effective. So as to solving formulas, that's not a problem. The other problem is the nonlinearity. We can have a nonlinear resistor, or the capacitor is a nonlinear one. That means that the capacity depends on instant charge or voltage at the capacitor. And that is a bit tricky. We are quite used to frequency domains, so more or less we have a lot of stuff for characterizing resistors, microstrip lines, transistors, or anything in the frequency domain. That's fine, but it gives little cues into the properties in time domain. So although we have a nice set of equations for most of elements at high frequencies like waveguides, coplanar waveguides, discontinuities, we have a few equations for characterization of that in time domain. So the weak point is not the mathematics behind that solves the equations. The weak point is a lack of reliable and good models. That's the first point. Second point, this is, in circuit theory, quite an easy way. So if you have a circuit with 10 capacitors and 17 inductors and one transformer, you get altogether some 30 equations, and that's easy to solve. What is less easy to do is solving a circuit which has distributed parameters. What distributed parameters is? Well, for example, we have there a transmission line, a piece of connection on the substrate, on the printed board circuit, and this piece is unfortunately in some cases comparable to the wavelength. At this moment we can substitute this by a model which mostly for a transmission line looks like a set of sections that are inductors and capacitors. Now remember, if you have this model, if you substitute a section of a transmission line with a model where this inductance is the inductance per unity length for 1 meter of the line, and the capacitor has the capacity of 1 meter of the transmission line, this would work in many aspects like the transmission line itself. But, so we will have there something which is called the impedance of the line, which for a lossless line is a square root of inductance over capacitance. Quite easy. And also this line has a phase shift which corresponds to the wavelength. So if you have this model, it mimics a transmission line as far as you do not get to a specific problem of this model. This is a model of a transmission line, but basically this structure is a low-pass circuit. If you decide to have a fifth-order low-pass circuit, for example a Butterworth, this is what you will realize in circuit theory. A ladder structure with inductors in this way and capacitors shunting each node between inductors in this way. So this is a low-pass circuit, which then would mean that this nice equation for the impedance in circuit theory, exactly called image impedance, would hold to more or less 1/2 of the critical frequency, that is the end of the passband. So this structure, which is a low-pass circuit, in fact has a frequency characteristic something like this. Frequency and transmission, be it V2 over V1, for example. So this is an ideal low-pass circuit. No transmission over, good transmission downstairs. But for a fifth-order Butterworth, you will get something like this. Now, once you approach the critical frequency, the structure no more works as a model of a transmission line. In order to overcome that, you can do quite an easy job. You can divide each section into two subsections so that we construct not a model of a transmission line composed of 1 meter sections, L and C, but we will divide each into two subsections. Then you would still get the same ratio between the inductance and capacitance, so that the impedance of the transmission line model is kept. But you would shift the frequency to a higher one. So this is easy. You can still have a model comprising inductors and capacitors which mimics the transmission line. Just you have to take care to get the cutoff frequency of the low-pass circuit sufficiently high. And now this is the tricky point. For a microstrip line for a line on a printed board circuit, this might mean that you, for example, include 100 sections. Because you have to break the transmission line into pieces that are really differential when compared to wavelength. So, still the ratio between the inductance and capacitance would be kept if you just take shorter and shorter pieces of the line, but you would increase the number of state variables, that is, the currents within inductors and voltages over capacitors. And with a simple printed circuit board which works at high frequencies, you can easily get to hundreds of those inductors and capacitors, and therefore this would get you to a situation where you have not 30 differential equations in the model, but hundreds. And yes, that would slow down the calculations significantly. So this is one of the problems that is difficult to handle using brute force. That was point one. Point two, shall you want to get a good, for example, frequency response of a circuit, of this one, for example, you would have to investigate the time domain behavior using differential equations. And for this circuit, if that was a linear one, you would possibly consider that there is a time constant R times C, just if you, for example, start to charge the capacitor through the resistor, this is the element which would govern the exponential behavior. Within the tau time, you would get from 0 to 63% of the full voltage, and so on. So if you would like to characterize that circuit in time domain, you would possibly carry out the integration for 5 time constants, 5 times tau. That is something that would, with a unity step at the input, you would get something like fully charged capacitor in 5 RC in the, so that's something you would fully charge the capacitor, and then you would take the circuit, sampled in time the voltage, and convert it using Fourier transform, and you would get easily the frequency response of this circuit. That's quite easy. Now, a remark, let's say you have a transistor. Let's get a low frequency model. So you have a transistor. This transistor, of course, has some stabilization, so possibly there is some RC circuit in the emitter. You would have some blocking capacitor in the input. You would have here some resistor connected to the voltage. You would possibly enjoy to have a stable voltage, so you would possibly put here some electrolytic capacitor blocking the input voltage. Now those capacitors would have quite different values, and some of them, like the blocking one, might be an order of magnitude or 2 orders of magnitude bigger than this one, and that would cause a long time constant of some parts of the circuit. So although you have a short time constant within the circuit itself, feeding circuits like capacitors, like DC sources, would quite often contain capacitors with big capacities, and you may still choose to make a full time domain solution of that, but that would require a lot of time. You can speed it up by first calculating the DC operating point, let's say starting the calculations from pre-charging all the capacitors to the operating point, and that would shorten your calculations and at the same time decrease your numerical errors within the calculation. So this was the first introductory talk. We can solve more or less anything in time domain, provided that we can describe nonlinear elements in time domain. A remark, Maxwell equations are differential equations, partial differential equations of the first order. So, for example, if you have finite difference time domain, you can handle nonlinear media quite easily if you can describe the nonlinearity. So if electric strength and electric flux density are not connected by a linear permittivity as a coefficient, you could handle that if you can describe the nonlinearity. So, as to time domain solution, this is quite simple. And for electric circuit, this is already handled by freeware like SPICE for simple circuits. Now, at high frequencies, you might run into real problems because the differences between blocking capacitors and capacitors really included in the circuit get several orders. The same point is that you would have to break transmission lines into models that are quite complex. And therefore, there are special tricks that are used to handle nonlinear circuits or media, and that is why I would like to describe you one of those important tricks, which is called harmonic balance method. But before we start to do that, we will have to, let's say, repeat some properties of a very important building block of that method, which is fast or discrete Fourier transform, because that is an important thing to rely on. And I will comment a little bit on FFT. We can watch fast Fourier transform like a special device which has an input and output sequence. So at the input we have a signal which is dependent on time. So we have the signal and we sample it at some points. Mostly we used equidistant